Hey, this is Jeremy Hewlett here with a new video for my channel, The Unsupervised Learner, and today I'm going to talk about decision trees. Here's the contents for this video. First, I'm going to talk about the basics of decision trees and cover basic terminology. Second, I'm going to talk about how predictions are made with a decision tree that's already built. And lastly, I'm going to give an overview of how one of the most popular decision tree building algorithms works. So the purpose of a decision tree is to make categorical or continuous predictions. It does this by creating a set of decision rules that lead to a prediction. Here's an example of a decision tree. The orange rectangles represent yes or no questions. The white arrows represent the direction traveled depending on the answer to the above question. The decision tree is traversed by following the rule that if the answer to the above question is yes, you go to the left, and if the answer to the above question is no, you go to the right. You continue down the decision tree path until you reach one of these green rectangles, and those rectangles represent your prediction. I'm going to talk about more about traversing a decision tree here in a moment, but first, let's talk about some basic terminology. The first question that the first decision is based on, which is the top rectangle here, is called the root. All the other questions in the decision tree are called nodes, or decision nodes. The last rectangle for each path in the decision tree are called leaves, and leaves are used to make predictions. Okay, so for the last part of our basic overview of decision trees, I'm going to cover their strengths and their weaknesses. One of the major advantages of decision trees is that they can handle interactions and nonlinear relationships. Another benefit is that the variables used by the decision tree to make predictions don't have to be scaled or normalized. Individual decision trees are also interpretable. I put in parentheses that this is kind of a strength, just because in practice, very few people will ever use an individual decision tree as a model. Most of the time we use multiple decision trees and aggregate the predictions in some way. So I say it's kind of a strength because the interpretability is lost when you aggregate trees, but with a single tree it's there, but really nobody really uses single trees for prediction. Okay, now I'm going to talk about a couple of weaknesses that decision trees have. Decision trees are prone to overfitting. If a decision tree is allowed to make an unlimited number of decision nodes, it can make way too many and start capturing randomness in the training data set. There are effective ways to prevent overfitting in decision trees, but I'm going to talk about those in another video. Decision trees are also not robust to changes in the training data. This means that if you change your training data set, sometimes even just a little bit, you could get a tree that's much different. However, this problem is mitigated when you're using multiple decision trees in a single model. Okay, so now I'm going to give a couple examples of how to make predictions given a decision tree. Here we have a decision tree that's designed to predict whether or not someone is a fan of the NFL. To the left, we have the data on our individual that we're trying to predict. If the answer to the question in the orange rectangle is yes, we go to the left. If the answer is no, we go to the right. Our first question is whether or not this person is off on Sundays. Since this person is off on Sundays, we're going to go to the left. Now we look to see if they know who Tom Brady is. They do, so we're also going to go to the left. Now, do they know what a two-point conversion is? Yes, so we're also going to go to the left, and we arrive at a leaf node. We know that that leaf node is now our prediction, so we are predicting that this person is a fan of the NFL. Here's another example. This person has Sundays off, so we're going to the left at the first node. They do not know who Tom Brady is, so now we're going to go to the right. We see that we're at a leaf node, which means that we have our prediction. We're predicting that this person is not a fan of the NFL. I'm going to do one more example just for good measure. This person does not have Sundays off, so at the root, we are going to the left. Let's see if this person watches NCAA football. They do, so we'll go to the right, and we arrive at a leaf node. So we're predicting that this person is a fan of the NFL. Now I'm going to talk about how decision trees are actually made. The main idea is to take data that's mixed in the target variable and to break it out into buckets that are more concentrated. Which piece of data goes to which bucket, of course, is decided by the answer to a binary question. The ultimate goal here is to create a set of decision rules or decision tree that classifies the data well without overfitting. Decision trees have a similar process that works for numbers as well. As I said earlier, decision trees can overfit. Here's our original decision tree for classifying these fruit from before. The tree could have continued going until all the leaves only had one type of fruit in it, but this probably would be overfitting. Obviously, we're going to want to build the best decision tree possible, build an optimal decision tree. But that's actually really hard. It's actually an NP-complete problem, which basically means that as our data sets get bigger and bigger, the difficulty or the amount of computational power required to find an optimal tree completely explodes and becomes an intractable problem. Since finding the optimal decision tree is intractable or just infeasible with any sizable data set, the algorithms we use have to use another method to be able to approximate a good tree or a close to optimal tree. And that's the approach that they use is a greedy approach, which basically means that you make the best move for the immediate step. Or in other words, at each node, you make the split that has the highest gain at that node. Here, gain just means the level of concentration that the split creates in the two buckets below it. We've had multiple decision tree algorithms developed, invented, and improved upon in the past. One of the first widely used algorithm was ID3, which was improved upon by C 4.5, which was then improved upon by C 5.0. Also, CART was developed, which stands for categorical and regression trees. And according to the people who wrote the documentation for sklearn, C 5.0 is approximately equal to CART. I don't know that because C 5.0 is not open source while CART is, but I'll take their word for it. Okay, so now I'm going to take a minute to briefly go over how the CART algorithm chooses a split. The CART algorithm at each node considers every possible split, which means that it looks at each unique value for each column. So here's an example data set. We're going to say that we have number of rooms, neighborhood type, and square feet as features in our model. So CART is going to look at each column, and it's going to look at each unique value of each column. So it's going to look at number of rooms, it's going to look at neighborhood type, and it's going to look at square feet and each of their unique values to see how well each of those splits the data. So we'll start by looking at the number of rooms. And here we're treating the number of rooms as a continuous variable. When CART looks at continuous variables, it gets each unique value of the continuous variable, and then it splits on the average of that. So for example, between 1 and 2, we would have 1.5. And so then CART will split everything that's below 1.5 goes to one direction, while everything that's above 1.5 goes to the other direction. Here on the left, I have the number of rooms sorted so that we can easily see the unique values. We have 1, 2, 3, 4, and 5. And so, like I said, we're going to be splitting on, we're going to try first if it's greater than 1.5, greater than 2.5, greater than 3.5, and greater than 4.5. And those are going to be the splits that CART is going to consider for the number of rooms sorted if the number of rooms is considered or treated as a continuous variable. And just for example's sake, if CART was treating the number of rooms as a categorical variable, which is probably more correct, then instead of splitting at the average of the two, it will just say, is it equal to 1, equal to 2, equal to 3, equal to 4, equal to 5, and it'll make those splits, it'll partition the data based on that. Okay, so after number of rooms, CART's going to look at neighborhood type. Obviously, neighborhood type is categorical, so we'll be using equality. So we'll say CART will first split, or not necessarily first, but CART will split on whether or not the neighborhood type is suburban, whether or not the neighborhood is urban, whether or not the neighborhood is rural. And those are the three distinct values under neighborhood type. It'll partition the data. It'll see how well the concentration of the data is after the partition compared to before the partition, and it'll consider that in its decision. So now CART's going to try partitioning on the square feet. So square feet is obviously a continuous variable, so CART is going to try the splits at the average in between the ordered unique values. So the first split CART will attempt is 1,150, the average between 800 and 1,500. Then it's going to try 1,650, the average between 1,500 and 1,800, and it's going to continue for each of the unique value sets, pairing more like. And so CART, like we've covered here, CART looks at every unique value for every column and it partitions the data. for each of those partitions, it measures how well the data is partitioned, how well the data is concentrated by that partition as compared to how well the data was concentrated before that. So we get these numbers, and the greatest concentration, the split that chooses the greatest concentration or creates the greatest concentration, is the one that CART chooses. So in that way, you can see how it's greedy. It's looking at one small piece of the problem, it finds the optimal solution for that one small piece, and it goes with that. And it does that iteratively until some kind of a stopping criteria is made. So it takes data, it partitions it into two pieces, and then those two pieces, it looks at those two pieces in the same way that it looked at the first piece, and then it partitions those two pieces potentially into two more pieces, and it continues partitioning and partitioning using this same logic, looking at every single possible split until the tree is fully built. So that's a very brief overview of how CART works, just a conceptual understanding. I'll make other videos that go a lot more into depth about how that algorithm works because it's so important. But I think that gives you a good conceptual understanding of how CART works. All right, so that's going to be all for this video. Decision trees is a huge topic. I'm going to make a lot more videos on it, so don't worry. And there's, obviously a lot of content on the internet on how to do that. But as I like to end my videos, I like to talk about the next questions, the next ways to do research, the next things to look up, more like. And so the first natural next question that I would have after watching this video is the details of CART, like I was talking about. We have an overview of how CART works, but how does it really work? I want to look at the pseudocode of the algorithm, maybe look at the actual open source code in sklearn. I'd be very interested in how the details of how CART works. Also, how do decision trees capture nonlinear relationships? I say that they do, but what's the logic behind that? What's the actual methodology, or I guess the actual conceptual understanding of how decision trees capture nonlinear relationships? The next natural question I'd have is what are the common ensemble methods? I said that decision trees aren't typically used by themselves. So what are the common ensemble methods that aggregate decision trees, and how do they work? What are their advantages and disadvantages, etc.? The next question is, how are regression and categorical trees different in the tree building and predicting? So, we have CART that can do categorical and regression trees. So what are the similarities? What are the differences? I'd like to know the details about that. Next is do you select the maximum depth of a decision tree, or the other tuning parameters that belong to decision trees? And what are the tuning parameters? And how are those selected, etc.? That's a really important question that wasn't covered in this video. And then lastly, why is scaling and normalization not required? What's the math behind that? I made that claim. It'd be nice to have a proof. Well, as always, I really appreciate you watching this video. I hope that you are coming away from it with a better understanding of how decision trees work, or a fundamental understanding of how decision trees work if you weren't familiar with them before. Go ahead and subscribe if you want to see more videos like this. Go ahead and leave a comment below if you have any questions or thoughts, and I appreciate your time.